The top side of a C175 piston is constantly fighting peak cylinder pressures and combustion heat that would literally deform it in minutes without help. And that help, it doesn't come from the top. It comes from underneath, in the form of a precisely aimed jet of oil you'll never see unless the engine is completely torn apart. Let's find out why that jet matters more than almost anything else in the lubrication system.
So think about that piston topside for a second. It's battling extreme combustion temperatures that could warp the steel in no time if left unchecked. You'd probably assume the primary cooling comes from the top down, right? Or maybe through the water jacket. But the real life-saving solution actually comes from a hidden, highly pressurized source right underneath it.
Section 1. The extreme heat problem.
When you look at the physical layout of the system, you've got these dedicated piston cooling jets alongside the oil supply grooves in the main bearing. Now, in your daily driver, you probably just think of oil as a friction reducer. It stops things from rubbing together. But on the C75, this lubrication architecture is actively pulling heat away from the hottest, most stressed component in the entire engine block.
You see, passive heat conduction, just letting the heat naturally soak through the piston skirt and out into the cylinder liner, simply isn't going to cut it on a platform with this much power density. So engineers use a piston cooling jet. It's a highly precise nozzle that sprays oil directly onto the underside or the crown of each piston. By blasting oil right onto that underside, the engine dramatically boosts the surface area for rapid heat transfer. It literally grabs that trapped combustion heat and carries it straight back down into the sump.
Section 2. Piston cooling jets explained.
To really grasp how this active heat removal works flawlessly thousands of times a minute, let's follow the oil. It starts its journey at the high-volume pump, shoots up through the main oil galleries, and heads to the crankshaft journals to keep those massive bearings alive. But crucially, it's also forced into these dedicated piston cooling jets. Every single stage of this process relies on absolutely continuous pressure. If that flow drops, even for a split second under heavy load, the results are catastrophic.
And this brilliantly illustrates the difference between standard machinery and mission-critical power. Think of standard splash lubrication like a commuter car that relies on whatever ambient air happens to pass by to cool its brakes. It works totally fine for a trip to the grocery store. But the C175 is like a high-performance race car. It uses targeted piston jets, which act exactly like active, dedicated brake cooling ducts, feeding high-velocity air straight onto the rotors. This system is actively engineered for sustained, extreme heat, not just a casual run.
Section 3. The localized blockage danger.
Let's put you in the technician's shoes for a minute. You're staring at your diagnostic screens. You've got a localized hot cylinder. One specific exhaust temperature is running noticeably higher than the rest. But you check the macro system gauges, and the overall engine oil pressure is absolutely perfect. The fuel system passes every test you throw at it. So what in the world is actually going on here?
Well, the root cause is often totally invisible until it's too late. We're talking about a blocked or misaligned piston cooling jet. This actually happens pretty frequently from a previous rebuild if the nozzle isn't lined up with absolute precision. Because that jet is choked off, it starves just one single piston of its critical cooling spray. So you get these localized temperature spikes, eventually causing piston crown deformation or scoring, all while the rest of the engine just happily hums along.
Here is the absolute most crucial takeaway. Your overall oil pressure can read completely normal while a single blocked jet quietly cooks one specific piston. You simply cannot rely on macro, system-wide oil sensors to diagnose localized microcooling failures. Those sensors only tell you the pump is pushing fluid. They absolutely do not guarantee that fluid is making it to every single microscopic destination.
Section 4. Pre-lube system protection. Now, while those cooling jets protect the engine during intense operation, we've also got to protect these massive, heavy components before the engine even turns over. Enter the pre-lube pump, mounted directly on the engine block. Because these engines often sit on standby for emergency power, all the oil eventually drains down into the sump over time. If you cranked this engine dry, the metal-on-metal friction before the main oil pump built pressure would cause brutal wear. So the pre-lube pump solves this by pushing oil into the bearings and the high-pressure fuel pump before the starting motor is ever allowed to engage.
And the engine's computer is incredibly strict about this logic. The pre-lube sequence operates automatically, right as part of the start cycle. It's going to run until the filtered oil pressure sensor reads at least 7 kilopascals, which is just about 1 psi. But here is the catch. It has to achieve that pressure within exactly 120 seconds. If it doesn't, the pump shuts itself off to protect itself, and you have to reinitiate the entire start sequence from scratch. It is a completely non-negotiable safeguard.
All right, let's summarize the major diagnostic mindset shift we've covered today. What you used to know, or maybe just what common instinct tells you, is that an unexplained exhaust temperature rise automatically means you need to start tearing into the fuel injectors or the fuel control valve. But what you know now is that it demands localized oil cooling diagnostics. You have to start thinking of the engine oil not just as a lubricant, but as a highly targeted, localized thermal management tool.
We've spent this entire explainer geeking out over incredible mechanical precision, from the exact alignment of a cooling jet to the strict 120-second logic of a preloop pump. But as we wrap up, it leaves us with a pretty compelling question. What happens when this level of unyielding mechanical precision translates to the electrical side of the machine? Next time, we're going to dive into the massive generator attached to this engine and find out why something totally invisible, like insulation resistance, requires the exact same level of microscopic diagnostic care. Thanks for joining me on this explainer, and I'll catch you in the next one.